Okay, and then you can start.
Okay. Well, good afternoon, Doc, and good afternoon, colleagues. I'm Samuel David Tay from Department of Mathematics, University of Cape Coast. Today, I'll be presenting on age-structured mathematical
You
model
can
for
start,
joint.
Osame. Please start.
Okay, so I'm Samuel David Tay. Please, can you hear me, Doc? Hello. So I'll be presenting on age-structured mathematical model for the joint disease modeling. I'm Samuel David Tay, Department of Mathematics, University of Cape Coast. The presentation will be guided by the following outline. We have introduction, few literature review, model formulation, simulation, and references. So, varicella zoster virus, commonly known as chickenpox, is a typically childhood illness that lasts within 4 to 7 days after an incubation period of 14 to 16 days. This virus is very common and spread easily through the respiratory droplets, similar like cold or flu. The chickenpox virus is unique because it stays in the body forever after infection. It can reactivate decades later as shingles, according to Kennedy and Gershon. Now let's look at that of parvovirus B19 virus. And throughout the presentation, I will be mentioning B19 virus. This is a small DNA virus that infects only humans and targets the red blood cell. It spread mainly through the respiratory droplet with high secondary attack rates on households and schools. Currently, there's no vaccine available for general public to prevent it, according to CDC. Many people get it without symptoms. So we said they are asymptomatic carriers. So you can get the disease without even knowing that you have it. This will be guided by the following model assumptions. First, we assume that individuals mix homogeneously at the start of an epidemic. 2, each individual can be infected by only one disease at a time. 3, recovery from a disease confers lifelong immunity. Then 4, no cross-immunity exists. Recovering from one disease does not protect against the other. So throughout our presentation and then our model will be guided by these assumptions. So based on that, we have the following model formulation, that's the methodology. The model considers two similarly transmitted diseases, that is varicella zoster virus, VZV, and parvovirus B19 virus, respectively, with the entire population given by this. This is driven by the following force of infection, as we have in lambda A given by VZV and lambda B given by this expression. So lambda B is referring to B19 virus and lambda A is referring to VZV virus. Now we have our compartmental models. We have S sub 11 susceptible to both VZV and B19. I sub 10 infected with VZV only. S sub 0 recovery from VZV and susceptible to BB19 up to R sub 11 recovered from both diseases. Now we have our model structure or the model formulation for these two diseases. We have the upper part, then we have the lower part. Now, the upper part, this part is representing individuals who are susceptible to both diseases. That is S sub SS. Now, since we are working with similarly transmitted disease and these two diseases are happening within a confined environment, the upper part is representing those with VZV, that is the chickenpox. So at the initial condition, we have the rate of transmission 1, I sub 10 is representing those who have been infected with the chickenpox. After recovery and treatment, they are now susceptible to B19 virus, that is S sub 01. Then susceptible, they will be infected with B19, that is J sub 01. Then they will be treated and recovered, move into the recovery compartment. Then the lower portion is representing those who have been infected with B19 virus. So I sub 01 infected with B19 virus, treatment and medication given to such a person is now susceptible to VZV virus, that is the chickenpox. Now, susceptible would be infected with J10, meaning that the person has been infected with the secondary infection of VZV virus. Then the person will be treated and both will be recovered in this manner. Now we have the model parameters. As I have here, transmission rate with fully susceptible individuals, B10 recovery from VZV, then K11 recovery rate of B19 virus in that order. Now, based on this, we have our model formulation. As we have the derivative of S sub 11, the T is given by the recruitment minus the forces of infection of VZV virus and that of B19 virus. Then we have the infected only with VZV virus given its equation with the following initial condition given as S sub 11 is greater than 0 up to the recovery R sub 11 with initial conditions greater or equal to 0. Now we can reformulate the previous slides in this format. So the model can be reformulated in this with the total population in each class. Total population in each class by dividing all the equations by n. The system of the ordinary differential equation in terms of proportion is given by below. So in our previous, we divide all this term by our total population, which is n. So we formalize it, and it is giving us this expression. As we have the derivative of small s sub 11 mu minus the forces of infection as a result of the proportion by the previous ones. Then we have the infected with VZV up to the recovery from VZV. Now, since we are working with this diseases, similarly transmitted disease with varicella virus and that of PB paravirus virus, we have incorporated age structure into it. Therefore, we need to extend the model to an age-structured format. So we say we incorporate heterogeneity in transmission. The population is therefore divided into two classes. We have children class with age less or equal to 25 years. Then we have adult class, age greater than 25 years. Individual transmission from children class to an adult class with this rate gamma. So we assume that an individual will be transmitted or move from an adult children's age into an adult's age with this gamma. Then we said that this accounts for the demographic progression between age groups. So this is our model structure for the age or the joint disease, which classified them into two layers. We have the first layer. This is for the children. Then we have the second layer is for the adult. As explained previously, we have S sub 11 exponent C is represent compartment with children. So these are compartments with children. And as explained previously, their force of infections are moving in this direction. Then we have the second layer, which I have S sub 11 exponent A representing adult compartment. So we have the adult compartment here. Now we need a transition from the child to adult is given by the lambda. Then we have the red transitions moving from this to this, then from this to this, meaning that from the infected, those who are infected with VZV, that's the secondary infection of VZV, coming into contact with children in a susceptible S sub 01 can infect them. So now based on that, we have this model structure from the, so this model equation is coming from our model structure in the previous presentation. So we have the derivative of S sub, this is the children compartment, giving us this equation. Infected VZV of children is giving us this up to the recovered one. Then we have the adult population, which is also giving us this expression equation. Then we have up to the recovered one. Now we have 4 transmission parameters associated with VZV, where we have alpha sub 10 CC, we have AC, we have CA, we have AC, we have AA. Then the same thing applies to PB19 virus with these transmission parameters. And it is important to know that whenever we have alpha sub A, CC denote transmission to a child from a child. And whenever we have CA denote transmission from children to an adult. So if we have AA here, it means transmission from adult to adult. And AC means from adult to child. That is the route of transmission, which has been explained in the diagram here. So this from here to here, meaning we have AC from adult to children. Then if I have CA, which is given by this parameter, is from children to adult. So the children or the child is infecting the adult. And then an adult which has been infected coming into contact with a susceptible children can infect such a child in that direction. So this is the route as explained previously in our slides. Now let's look at the quantitative behavior of the disease. First, we talk of the disease-free equilibrium. We said the disease-free equilibrium is obtained by setting all the infected compartment to 0. This states the population consists of entirely susceptible individuals with no active infection. So we set all the infected compartments to 0. Then we solve the remaining as a steady state system. Then we said that at equilibrium, the derivatives are set to what? 0. So it means that if we have the first system of our equation, the derivative of S sub 11, the T, summing at disease-free, summing them together will yield this expression, meaning that all other compartments will end up to 0, giving us this expression. Then we set this one to 0, we solve this, and we get S sub 1 as this. Then we said, therefore, the unique disease-free equilibrium is given by 1. All the other compartments are 0. Now let's look at positivity of solutions. We show that the solution of the model remain non-negative for all t greater than 0. Consider the first equation like this. We said the derivative of S sub dt is given by the first equation in our system of equation. So we said if S sub uu is equal to 0, then it means that all this part will be 0, this part will be 0, leaving mu, and the derivative of this is greater than 0. Similarly, applying to the other compartment, if I, the infected compartment of I sub 10 is equal to 0, when you find its derivative, it's either greater or equal to 0. Therefore, we can say that the same argument is applied to the remaining compartments. Therefore, any solution with non-negative initial condition remain in our 8-dimensional space for all t greater than 0. We further move on to invariant region. To show that the model is biologically consistent, we demonstrate that its feasible region is positively invariant. This ensures that all state variables remain non-negative and that the total population stays bounded at all time for t greater than 0. So we let the total population given by this. So we have n of t is given by the summation of all the state compartments given by this. Now, when we sum all the state compartments at the system of equation 2, it yields these results. We solve this differential equation, and as n approaches 1, as t approaches infinity. So it means that our system is bounded by this expression as t approaches infinity. Therefore, the feasible region is in omega, which is given by x belongs to the 8-dimensional space, such that the entire human population is less or equal to 1. Then we further look at the basic reproduction number, R0. We apply the next generation matrix. We let F represent new infection and V represent transitions. Then we take the infected compartment as given below. The infected subsystem can be written as the derivative of y dt, which is given by the f of y minus v of y. So our f is given by this, that is the new infection, and our v is representing our transition vector. Now we compute the Jacobian matrix on f and v. So the Jacobian matrix on this f is this, and the Jacobian matrix on this v is given by that. From here, we find f and v inverse, which is given by this expression. Then we have the eigenvalues is f times v inverse. So we have lambda 1 as this expression, lambda 2 as this expression. Lambda 1 is representing our VZV virus, and lambda 2 is representing our B19 virus, since we are dealing with 2 viruses. So the maximum eigenvalue, which is our R0, is given by this, where this represents VZV, that's the chicken pox, and this one also represents the B19 virus, respectively. All other parts are 0, 0. Now we look at local stability at disease-free. Here we apply Routh-Hellweg criterion, and we apply the Jacobian matrix on the disease compartment. So this H is giving us this expression as a result of the Jacobian matrix on disease compartment. Then we have the eigenvalues of the Jacobian matrix are given by this. However, we have that if our lambda 1 is equal to this up to lambda 2, the remaining eigenvalues are negative. Therefore, we can argue that if our R0 is less than 1, all eigenvalues are negative. It implies that our disease-free is locally asymptotically stable. If our R0 is greater than 1, at least one eigenvalue positive is unstable. We further also check the global stability to ascertain the behavior of how the disease transmits in the system, backed by this theorem. So we are saying that if our maximum R0 is less than 1, Then the disease-free equilibrium, which is given by this set, is globally asymptotically stable in omega. However, we let our n, which represents the summation of all the state variables given by this. Now, summing the equation 2 of our system of equation and finding the derivative will give us this. Now, finding the derivative of this gives us this expression. Hence, as t approaches infinity, our entire population is also approaching 1. And we can say that in omega, it is positively invariant. It is not concluded yet. We need to also check how the disease further behaves. So we apply the Lyapunov function. So we consider the linear Lyapunov function given by L is equal to the infected compartment. So we group them into one. I1 represents the infected compartment of VZV. Then I2 represents the infected compartment of B19 virus. We find the derivative of L1 and L2. Then from our model equation, we have this. So our model equation from equation 2, that's the system of equation 2, the formalized one. We have the derivative of L1 is given by this expression. Now you could agree with me that at disease-free equilibrium, this part will be given by the I. Therefore, we have S sub 11 plus S sub 10 should be less than 1. We also have for the L1 to be given like this, we have V alpha V minus B beta plus mu times our I1. So this guy is given by this one. So we have our alpha V, which is here, which has left with this part, and then we have this. Then the whole of this and this is our I, which we have represented or we have let it. Similarly apply to the L2, which is the B19 virus. It's also giving us this. Now we substitute our R0 into it and we obtain the following. So with the derivative of the Lyapunov function is bounded by this expression beta plus mu, our R0 minus 1 times the I1 plus the B19 virus. Now we say that if our R0 is less than 1, and it implies that this one is less than 1, B19 is also less than 1. So the derivative of the Lyapunov function, if it is less than or equal to 1, we can say that the derivative of I1 is equal to 1, which implies that our I1 is equal to I2 and they are all equal to 0. Then by Lasser's invariance principle, we let M, which is equal to X in omega, such that the derivative of the Lyapunov function is equal to 0. Then we can say that from our derivative, which is equal to 0, we have that the infected compartments are equal to 0 at disease-free equilibrium. Consequently, we can say that the derivative of all other steps is also approaching 0, which implies that this state variables at its derivative is also approaching 0. Now we can have our n approaches 1, and it follows that as S sub 11 approaches 1, hence the only invariant region set, that is E0, is given by this expression as 1, 0, 0, 0. By Lasser's invariance principle, the disease-free equilibrium is globally asymptotically stable when our R0 is less than 1. Then we look at the endemic equilibrium of our system. Here there are 3 types of endemic equilibrium for the system. We have a situation whereby there is only VZV present in the population. Then we have BB19 present in the population, or both diseases are present in the population. Here there is a distinction. Based on our assumption, we said that there's no way one can be what? Based on our assumption, we said that the disease affects one person at a time. So here coexist simply means that both diseases are in this population. They exist, but it doesn't mean that the person has been infected with VZV, and at the same time, B19 virus. So we said they coexist in the population. Now we investigate the endemic equilibrium by assuming that the population is being invaded by VZV. However, at its equilibrium, the derivative from state I to state J is equal to 0. The infected and that of recovery are all equal to what? 0. Now, at equilibrium, we reduce the subsystem, that is equation 2, into this part, where we have mu minus alpha V is equal to 0. Then we have this expression is also equal to 0. Now, the system admits two solutions. Well, first, we have trivial solution. We look at the situation whereby the infected compartment or the one that is being affected with VZV only is equal to 0. And when that happens, it means that our susceptible is equal to what? 1. Therefore, this corresponds to the disease-free equilibrium, and hence the entire population is susceptible to VZV, which means that it is trivial. Our result is not yielded. So we look at a situation whereby our infected compartment is not equal to what? 0. So the second solution of the system C is obtained when our infected compartment is not equal to what? 0. Then it implies that the system of equation from the first part, this part, we solve it algebraically. And the first part is given by this expression. So we said our S sub 111, the exponent 3 here is talking about the third form of the endemic equilibrium of VZV. Is given by this expression. Then S sub 01 is also given by this expression. Then I sub 10 is given by this expression as our endemic equilibrium for the VZV only. Where all other states or all other state compartments are equal to 0, that is I sub 10 up to the recovery are all equal to 0. In this case, we say that the population is no longer entirely susceptible, but the positive fraction of individual is infected with VZV. And it is clear that our S sub 11, I sub 10, then S sub 01 are positive, provided that if our R0 for VZV is greater than 1. Then we are saying that we look at the endemic equilibrium for PB19 virus. We said that since the system, that is equation 2, is symmetric with respect to VZV and PB19 virus, we derive the equilibrium solution by assuming that the only PBV virus has invaded the population and it reaches its equilibrium. And therefore, in this case, we obtain the following equilibrium at endemic equilibrium for those infected with PB19 virus only. So we use the same idea as we did in VZV to also find the endemic equilibrium by looking at the trivial and the non-trivial, and we solve them algebraically, and this gives us this expression. So the first one is for PV, the second and the third. All other compartments are 0. Therefore, we can say that the endemic equilibrium of the only PB19 virus is greater than, if R0 is greater than what? 1. It happens if and only if the R0 of B19 virus is greater than 1. Now, since we are looking at the two diseases, 1, the homogeneous parts, and 2, the heterogeneous parts, we can also extend the transmission behavior to the age structure. So we have the conditional prevalence of age structure disease. So we said the conditional probability provides a mathematical foundation for analyzing how prior infection with one disease influences the risk of acquiring another, then ensuring that the joint disease model reflects the true epidemiological dynamics of population. Since we are dealing with two diseases in two different age groups, we can define 4 different conditional probabilities for each group, then they are 1. Here we are looking at the probability that the first person is infected with VZV, given that it is susceptible to B19 virus. The second probability is also looking at the person is infected with VZV, given that the same or it is also infected with B19 virus. Then we also look at the probability that the first person is infected with B19 virus and later susceptible to VZV virus. Then we also look at the probability that the first person or the person is infected with B19 virus, given that is also infected with VZV virus. So why do we need this? We need this to look at the age and the age differences between how the disease moves or how the disease spread within this. As we look at the first one, which is treating the disease in isolation, here we look at the situation whereby we incorporate age structure. We are considering age in this type of the modeling. Therefore, we need these conditional probabilities to estimate whatever we want to do. So as I explained, these are the explanation for that. Further, we also look at the equilibrium for these joint diseases. From the steady state solution, the following joint probabilities are defined. We have E00, meaning that they are susceptible to both diseases. E01 means that they are susceptible to VZV and infected with B19 virus. And this is similar to what we've discussed previously. Then the E11 is infected with VZV and susceptible with that. In that order, up to E111, which means both are infected with V and recovered later infected with B19 virus, respectively. Now, the conditional prevalence for each group. We look at the conditional prevalence for each group and can be expressed as this, as what we have. This expression is the same as what I have presented here. Probability that both are infected. We have, it is the susceptible with respect to exposed with VZV, infected with B plus exposed with both diseases in that order. Here we said that the equilibrium solution of the age-structured joint disease model is obtained numerically by replacing the person-to-person transmission WAIFW. So we call who affect or who infects the other matrix with the WFI matrix construct from the social contact matrix. Now optimizing the probability proportionality factor K sub Q over the plausible range to match the model-based conditional prevalence with seroprevalence data. So here what we are trying to do is that after we have developed our conditional probabilities, what is next? Now our next problem is to formulate this into MATLAB codes to simulate or find out how the disease transmits between the age groups and see which of them is infected. So based on that, we have our following parameter and its values. And these parameter values are due from the Bayesian seroprevalence data in that order. Now we have our model simulation. Here, what did we do here? We look at these two parts of the simulation. First, we look at the homogeneous part, whereby the person is infected with either VZV or B19 virus. So we simulate this, and what did we see? We look at a situation whereby both R0 are greater than 1, meaning that with the given parameters, supposing the system or the disease can invade the population, how does the transmission moves? We could observe that those with this disease, that is VZV, I sub 10, is higher as compared to those infected with I sub-01, that is B19. So this color is representing the B19 virus, and this color is representing the chickenpox, that's the VZV virus. And you could observe from here that this is very high, meaning that the chickenpox can spread at a faster rate as compared to the PB19 virus. So according to literature, the PB19 virus spreads slowly, but the chickenpox spread rapidly. And our simulation is giving us this expression. All other curves are the secondary infections, as we have the secondary infection for J sub-01, which is given in this color. Here we look at a situation whereby you have been infected with the secondary infection, susceptible or infected with secondary infection of VZV, and we have infected with secondary infection with ISAP 10. And this is the dynamics. You could observe that if we simulate only those infected with B19 virus, which is in the blue color, given like this, it surpasses all the other secondary infections. So what we have here, we said the susceptible decreases rapidly due to sharp increase in VZV infections. PB19 infection remains relatively low because of its lower transmission rate. So according to research, the B19 virus spreads slowly. That is why we said somebody can even have the disease without knowing. So we said it is asymptomatic. You can have it without the idea. But as for the chickenpox, within 3 to 4 days, it started to manifest its symptoms. So this simulation is also giving us the fast and the rate at which it spreads. Then we said the peak proportion of the individual infected with VZV is higher than those in the infected compartment. So if we can see this, those in the chickenpox is higher than the mere one of the B19 virus. Later, we also perform some changing of the parameters, or we vary the parameter to see what might happen. So we look at the situation whereby the R0 for VZV is less than 1, and R0 for PB19 virus is greater than 1. And we could observe that from literature, the B19 is higher than the chickenpox. As a result of the chickenpox is dying, and the B19 virus is also prevailing or invading. So we said when our R0 for VZV is less than 1, the VZV failed to invade, causing the VZV-related compartment to remain at negligible level. So this blue line is representing our VZV, which is the chickenpox, and this line or this curve is representing our B19. The majority of the population moves through the B19 infectious phase while VZV remains suppressed, as we can see from here, when our R0 for VZV is less than that. Then we also look at a situation whereby we also change the parameters or vary the parameters for VZV and BB19 virus in such a way that both R0 should be what? Equal, and see how fast the disease spreads. And you could observe from this simulation that those with the infected compartment for I sub 10, that is the chickenpox, spread very faster as it moves in this direction, with a peak almost approaching the 1. Then you can also observe that the chickenpox is also hanging below. So even though when the R0 for these two diseases are the same, from our simulation and our mathematical simulation, is telling us that the chickenpox spread very faster, and this is our threshold. So we assume that the blue is for VZV and the red is for B19, and our R0 figure is given by 1010. So we are assuming that, okay, what if these two diseases invade the population? Which of them will transmit faster and which of them will transmit slowly. And this simulation is telling us which of them will transmit faster, as in VZV, and the similar one as in B19 virus. So as this expression is in, we observe that though the two diseases have equal basic reproduction number, the rate of transmission plays a crucial role. We also observe that the peak proportion of individuals in VZV infectious classes is higher than those in the BB19 classes. We later also look at the age structured, that is the incorporation of the age structured into these two diseases. So the first part is looking at the homogeneous part, and this simulation is also looking at the heterogeneous part by incorporating the age specific into the mode of the transmission. So what did we do here? We modeled two similarly transmitted childhood diseases, that is varicella zoster virus, VZV, and parvovirus B19 virus. Homogeneous mixing models are unrealistic, as I explained earlier on, for large population. Therefore, we implement an age-structured model distinguishing children and that of adults, and children less or equal to 25 years, and adults greater than 25 years. So for the first one, we are looking at the homogeneous, looking at VZV and B19 virus. By this time, we are trying to incorporate age specific into it to see how the disease transmits within these age groups, and which of them transmit faster, which of them transmit slowly when age is incorporated into it. What did we do? Let's look at the computational approach. We define system of ODEs tracking 16 compartments, 8 for children, 8 for adults. Then how does the simulation goes? We perform a time horizon of 100,000 days to ensure equilibrium. So this one, the simulation is performed in such a way that it should be very long, so that when at its equilibrium, what will be the transmission rate of these two diseases? But in the previous one, we look at a short time. Let's simulate and see what might happen within a short time. Now, this one is telling us that let's simulate and see in the long time what might happen. How did we go? We said the demographic parameters are based on Belgian population data. Direct contact data was scaled by proportionality factor, Q. We perform a grid search to minimize the difference between the model and the real seroprevalence data. And what do we mean by grid search? We say it's a parameter estimation method where multiple candidates are tested systematically, and the set giving the best agreement with the data is selected. So here we select a lot of or several parameters. Then we simulate it a very long time, such that both diseases will reach its equilibrium, and see both diseases, how does it transmit? And as explained, the estimated conditional probability obtained from seroprevalence data. So after our simulation, this is what we obtain. We obtain that the probability that both are infected in children, we have 0.92. In adults, we have 0.99. Probability that the person is infected with VZV, that is chickenpox, and later infected with B19. In children, we have this result, which is 0.47. In adults, we have this result, which is 0.73. Then probability that the same person is infected with B19, later infected with the chickenpox. In children, we have 0.92. In adults, we have 0.99. Then probability that the person is infected with B19, later susceptible, or later susceptible with VZV. In adults, in children, we have 0.46, and in adults, we have 0.71, respectively. So we said there is a strong correlation, which indicates that the B19, being the slower disease, remain visible over a long period than VZV. And I will explain this later in our subsequent presentation. Now, based on that, we need to compare our parameter set. So as I said, we compare 4 parameter sets, that is Q values, to find the best fit for the contact matrix. So first we set obtain from the seroprevalence data. So we get our seroprevalence data from Belgium data. Then the set 2, that's set 2 to 4, is a hypothetical scenario. So we assume, okay, what might happen if this data is given, or we have this data, we have this data. What would be the assumption or the hypothetical simulation C? So if you see the first column are the true data from the Belgium data. Then the same thing. So if you see this column, you could observe that it is the same as what we have here. It is the same as what we have here. So this is what we have here for children which are less than that and children which are greater than 25 years. And column 2, 3, and 4 are our assumptions or hypothetical data which we used. Then I said, okay, at the long run, what will be the rate at which the disease will transmit and see? Per our simulation and then the model simulation, what did we see? We see children less than 25 years. We could observe that those who are infected with B19 virus is higher as compared to those who are infected with the chickenpox, which are lying approximately 0. Now let's move on to those who are greater than 0. You can observe that those who are infected with B19 virus is also higher, and those with chickenpox is less, and majority of them are recovered in that order. What is happening? Those who are less than 25 years, which is the children, is lesser than those who are above 25 years. So this quickly blows my mind. And I ask myself, why is it that in a previous simulation, I was seeing those who are infected with chickenpox are greater, or they are spreading faster as compared to those who are infected with B19 virus. So this gives me an article which is written by Young and Goshin. Later revealed that since the BB19 virus is asymptomatic, it means that the person will accumulate the disease within the person for a long period of time. Secondly, it doesn't have vaccine. So the person will be having the disease unknowingly. But as for the chickenpox, the moment you have it, within 4 days, 5 days, its symptoms and signs are shown. Likewise, there is a vaccine for it. So when that person takes the vaccine, it confers long life immunity for such a person. Therefore, in the long run, when you simulate or you perform your simulation, the B19 virus will surpass the VZV, that is the chickenpox virus, as in the long run. So what did I see? I said that the age structure dynamics of VZV model in children given by this, the risk of infection is significantly higher for PV19 than VZV and higher for adults than children. So I asked myself, we asked ourselves, why is it that it is higher in adults than in what? Children. And later article also revealed that since when somebody is having the disease, it transmits the disease from child to adult. So you could observe that the disease transmission is moving, that is gamma, which I have here. The model diagram, this gamma is telling us that, yes, we are moving the disease from child to adult in that direction. That makes it to happen that though the person is developing with the disease, and as time goes on, based on our assumption, we realize that the disease stays in the body for a longer period of time and it doesn't go. So what happens? We later move on to extinction time. We realize that the numerical simulation indicate that the expected time to extinction is shorter in the younger group than in adult group. So as you can see, in the children, you can see that the highest peak is 0.3. Then in adults, you can see that, in children, the highest peak is approximately 0.024 thereabouts. Then in adults, you could see that the maximum peak is approximately 0.4, meaning that the extinction time, the rate at which the disease will go to zero in children is lesser than the rate which the disease will go to zero in adults. So it will take a long time in adults for the disease to die out, and it takes shorter time in children for the disease to die out. Then we have the peak of the epidemic in the older group is higher compared to the younger group. This is due to the accumulation of susceptible individuals who aged up into adult category without being infected as children. So as I said, or as explained previously there. Now let's look at our conclusion. We said the joint disease model of VZV and PP19 reveals an important interaction between similarly transmitted infection. Conditional prevalence is essential for capturing sequential infection risks and aligning model with seroprevalence data. Age-structured modeling improves realism by distinguishing children less than 25 years and adults greater than 25 years, reflecting different transmission patterns. Numerical simulation shows that VZV has a higher transmission and peak prevalence compared to B19 when they are not with similar R0. Equilibrium analysis confirms disease-free is stable, endemic exists when our R0 for VZV is greater than 1 or R0 for B19 is greater than 1. This work shows that understanding the... Thank you. Here are some of my references. Thank you, colleagues. Hello.
Okay.
All right, good. Guys, any questions from any of you?
Okay, Sammy, thank you, Doc. Sammy, I have 2 questions.
Okay.
Yeah, please, let's go to page 16. The derivation of the disease-free equilibrium.
Okay. Page 16.
Yeah.
Slide 16.
Yes,
Slide 16, yes.
Okay.
Please, we derived that the disease-free equilibrium and the disease-free, all of them were to be. Please, can you go to 15, page 15? Yeah.
Page 15.
Yeah. Miss, please, I want the disease-free. I think the page number I wrote is quite wrong.
The disease-free is page 16.
Yes. So you introduce that at the disease-free, the infected compartments are all 0, which I10, J10, I01, J01, all equal to 0. But do we include the recovered compartments as part of the infected groups?
At disease-free, the disease is not even infecting, so there is no recovery.
Good. I'm asking that. Do you include the recovered compartment as part of your infected compartment in the
No.
derivation?
Look at it. This one, ISAP10 is primary infection from chickenpox. JSAP10 is secondary infection from chickenpox. ISAP01 is primary infection from B19 virus. Then JSAP01 is secondary infection. So if you look at the model diagram as I have here, I have primary infection, secondary infection, secondary infection. So when the person is infected, primary, first time infection, the person will be treated susceptible to B19 virus, infected, treated, and recovered. Then the same thing applies to B19 virus, infected, treated, susceptible to chickenpox, infected with chickenpox, treated, and then they will go back to, recovery.
But the substitution to 0 on the recovered is where I had the issue with. And you said in the long run, the total population, N of T, approaches 1. Why?
Yes.
As time approaches infinity. Yes.
Okay, as time approaches, so that's a
Yeah.
very nice one. So at disease-free, we set our derivative here to be what? 0. Okay. So what do we have here? It will left with the reformatted one here. So it will be mu minus mu sh. I'll factor this one out. This will give me 1 minus s of h. Then I'll solve for s of 1 and it will be equal to 1. If I factor this mu of h out, it will be 1 minus s sub 1. You get it? Then I divide by mu and I isolate this and it will give me my entire or at disease-free that would be susceptible to 1. Why?
But why do you equate this the disease-free? Please go back.
coming.
Why do you equate it to 0?
Why do I equate it to 0?
Yes.
So we said at disease-free there is
No, the S over T, that one. Please go back. Yes.
this one. This part is 0. We said, and solving the remaining steady state at equilibrium, we said the derivative equal to 0. So this derivative is equal to 0 at disease-free. So this is equal to 0. Then we solve for our state variable.
Okay. And the last one. Please let's go to page 43. Okay, so the first simulation you did was on the short term, and we could see that the time interval for the simulation was done over months, right?
Yes.
I think barely 11 months from the first one, the short term.
Yeah.
But we are also seeing in this long term that it was also simulated over barely 11 months.
Yeah.
But you assumed before your simulation that you are using 100,000 month or something like that. 100,000 days.
100,000 days.
Very good. And having these 11 months for the long-term simulation and the short-term simulation also 11 months, are there any differences?
That's very good
Because in the
question.
long term, we should simulate over ideally years, because we're going to have around 27 years if we are using 100,000 days for the long term. But if we are using months, which is barely 13 months, to depict the two scenarios, I think something is quite unclear over there. Can you clear for me?
Nice question. What we are trying to do is that though we are doing it within the specific 1 year time, okay, the period is 1 year, but our time span, that the simulation span, we want to expand it in such a way that both diseases will reach its equilibrium. That in the long run, but the other one in a short run within the same 1 year. So it's like this. We have, let's say, 2,000 people. In a long or in a short time, we are considering 1,000 people to do the simulation. In a long run, we are considering 2,000 people to do the simulation to see these diseases, how they will end up in the long run. That is why, though we are using the same specific 1 year simulation, but we are looking at the long run, what might happen within these two diseases. That is why I use 1,000 days to do that similar, or 1,000.
100,000.
100,000 parameters to do that simulations. And if you don't mind, I can show you the Python course and the MATLAB course, and I can explain more from the MATLAB course as given. If you don't mind, I can share that.
I'm fine. Thank you.
One also.
Thank you, Doc. Please, Doc, I'm done.
Okay. Any other person?